You know, as a functional safety engineer, my entire job is to prevent disasters in places like massive oil rigs, sprawling power plants, and complex chemical facilities. We have to answer one huge question. How do we prove our automated safety systems are actually going to work when we need them most? So today, we're going to pull back the curtain on the single most essential tool we use to do that, the SIL Verification Calculator.
All right, let's just jump right in. I want you to picture a high-pressure reactor, right at the very heart of a refinery. You've got all these layers of control, you've got alarms, but what happens if all of that fails? What is the one thing, the absolute last line of defense, standing between a totally normal day and a complete catastrophe?
Well, that last line of defense is this, a safety instrumented function, or what we call a SIF. Think of it as an automated safety loop, and it's got three main parts. First, you've got your sensors. Things like pressure transmitters, out there sniffing for any sign of a hazardous condition. They're constantly feeding data to a logic solver, which is basically the brain of the whole operation. And if a dangerous line is crossed, that brain makes a split-second decision and commands the final elements, usually these big emergency shutdown valves, to slam shut and get everything back to a safe state.
So yeah, these SIFs, they are our last stand against disaster. They just sit there, silently, in the background, waiting for a call to action that, let's be honest, we all hope never ever comes.
And that, right there, that brings up the billion-dollar question. This system, it might not have to do its job for years. So how can we be absolutely certain, with cold, hard engineering proof, that it will work perfectly in that one critical moment?
The answer isn't just crossing our fingers and hoping for the best. It's a really rigorous mathematical process that's actually required by global functional safety standards, things like IEC 61508 and 61511. These standards force us to prove, quantitatively, that our design is safe enough for the job.
To actually do that, we need a way to talk about safety performance. We need a language. And that's where two absolutely key concepts come into play, SIL and PFDavg.
So SIL stands for Safety Integrity Level. It's really just a way of classifying how much risk reduction we're getting. And as you can see right here, there are 4 levels. Every single step up, from SIL 1 to SIL 2, or from SIL 2 to SIL 3, represents a 10-fold increase in safety performance. That means a SIL 3 system is at least 100 times more reliable than a SIL 1 system.
And we measure that performance with this metric, PFDavg. It stands for Probability of Failure on Demand. To put it really simply, this number is the chance that our last line of defense will fail us. Our entire goal as engineers is to drive this number as low as we possibly can.
Okay, theory's great, but let's make this real. We're going to walk through a super common engineering challenge, verifying the design for an overpressure protection system on a refinery reactor. And to do that, we're going to use our most essential tool, the SIL calculator.
The process is actually pretty straightforward. First, we define our whole system and we gather up all the data we need. Second, the calculator does the heavy lifting. It runs all the complex formulas to figure out the PFDavg. And finally, we just compare that result to our target to see if the design is actually safe enough.
Now, the calculator is only as good as the data we feed it. We need these key inputs, like the dangerous failure rate for every single component, which tells us how often we expect it to fail in a bad way. We also have to input our maintenance schedule, what we call the proof test interval. We have to account for how smart our devices are with diagnostic coverage. And of course, we model things like redundancy and other vulnerabilities.
Okay, so for our reactor problem, a risk assessment was done, and it determined that a catastrophic failure would require a risk reduction of at least 100. What that means for us is that our design must achieve, at a minimum, a SIL 2 rating. That's our target, that's the goal.
So, we take all the data for our proposed design, the specific sensors, the logic solver, the valves, and we plug it all in. We hit calculate, and the software just crunches all the numbers based on the formulas from the IEC standards. And for our system, it spits out this result, a PFDavg of 00018.
So what does that number actually mean? Well, a SIL 2 target needs a PFDavg somewhere between 0.01 and 0.001. Our result, 0.0018, falls right smack in that range. So what does that mean? It means our design passes verification. We have quantitatively proven that it is safe enough. But you know, our job doesn't just stop with a passing grade. The real power of a SIL calculator is that it lets us play what if. It lets us explore all these different engineering trade-offs between safety, maintenance, and of course, cost. Let's test this out. Imagine management comes to you and says, hey, we want to save some money by extending the proof test from 1 year to 3 years. Okay, we plug that one tiny change into the calculator, and look what happens. The PFDavg just skyrockets to 0.012. Our design, which was a perfectly good SIL 2 system, now fails to even meet SIL 1. This is an incredibly powerful way to show exactly why those maintenance schedules are so critical for safety.
Okay, now let's flip it around. What if we invest a little more money in a more advanced pressure transmitter, one with way better self-diagnostics? We change its diagnostic coverage in the calculator from 60% to 95%. And wow, not only does the system still pass SIL 2 with flying colors, but its PFDavg drops all the way to 0.0008. That actually pushes it into the SIL 3 performance category. We've made a huge improvement in safety just by choosing a better component.
So this brings us to the final, and I think the most important part of all this. Why do we go through all this trouble? Why does this matter so much?
The reality is, we rely on specialized software because the math behind this is incredibly complex and the stakes are just way too high for human error. These tools let us model all kinds of different designs, optimize them super quickly, and, this is crucial, produce a report that we can audit that proves to regulators and to ourselves that we have done our due diligence.
At the end of the day, SIL verification isn't just some academic exercise. It's the engineering discipline that turns a safety concept into something real, something quantifiable, something provable. It's how we make sure that our last line of defense is actually going to be there when it counts, protecting our facilities, protecting the environment, and ultimately protecting human lives. It really is engineering safety by the numbers.